Hello again, Chapter 8. We're going to be talking all about rotation. Alright, any object that spins in a circle about an axis is undergoing circular motion. Right? So, look at this Ferris wheel, right? It's going around and around and around. Well, right here is its axis, right? Torque wrench, right? Right here is the axis and it spins this way, right? Tire on your car, there's the axis and it's spinning. Alright? Circular motion depends on two types of speeds. Tangential, which we know as linear speed, which is what we've talked about all up until this point. And now we're going to introduce a new one, rotational speed. Well, linear speed, as we know, is distance over time. Alright? Well, look at these pictures and figure out which one of these bugs is going faster. Alright? Well, to do that, we got to think about, well, how much distance are they covering? Alright? So this little bug is covering a circle that's about this big. But this bug is covering a circle that's that big. Right? So who's going the bigger distance? Alright? This little bug on the outside of the circle is going a bigger distance because the record is rotating in the same amount of time. Alright? But being out here at the edge, the little bug covers more ground. Alright? Think about it when you were little, riding on the merry-go-round at the park, right? Were you the scared kid holding on to the post in the middle, or were you the wild child hanging on the end, woohoo, hair dragging the ground? Alright? Why did you get on the edge? That's where it's going faster. Alright? But that's linear speed. Okay? Because you're covering more distance around, right? That circumference of the circle, it depends on how big the circle is as to how fast that linear speed is. Okay? Well, now rotational speed, right? That depends on how many times that object goes around the circle, right? So how many times that merry-go-round went around, right, in a certain amount of time. Alright, we know that as rotations or revolutions per minute, per second, per unit of time, right? Keep your eye on this, because in physics, the unit of time we usually use is seconds, okay? Now, rotational speed is given by this Greek letter omega. Looks like a curly W, okay? Well, how can we relate our two speeds? Okay? Well, what did I say that linear speed depends on? How big that circle is, right? And all parts of that record or that merry-go-round is rotating in the same fashion, right? So here we go. The radius of the circle times that rotational speed gives you your linear speed, okay? And if you don't remember how to get the radius of the circle, here you go, right? The diameter is the whole length across. The radius is half that, okay? Well, we know from past chapters that you have to overcome an object's inertia to make it move. Well, making something rotate is no different. Now it's just called rotational inertia. Alright? Now before, inertia was just based on mass. Right? But now rotational inertia is going to depend on not only the mass of the object, but how that mass is distributed around that axis. Okay? Watch the video and check out the picture just to see what I mean. Alright? So the greater the inertia, the harder it is to change a rotational state. Ever wonder why these tightrope walkers have such big sticks? Right? Why don't they carry a little stick? The big stick means their mass is more distributed. Right? It's harder for them to change their rotational state. Imagine you're walking across a log as a kid. What did you do? You held your arms out, right? Try walking across that log like this. Any little and you're going to splash in the water, right? Rotational inertia. Okay? Well, we talked about rotational inertia depending on how the mass is distributed around the axis, right? Check out this picture, because we've got 3 different axes of rotations given by the dotted lines, right? Actually, pick up your pencil and try this to see what I mean. Okay? It'll really help you understand. rotational inertia is different for different objects of different shapes and different mass distributions. Now don't panic, you don't have to know everything in the picture. It's just to give you an example, a working knowledge of what I'm talking about. Okay? So torque. Okay? Torque is a force that causes a rotation. Okay? So here we have a wrench trying to loosen this stubborn nut. Alright, so we can get the bolt out of this whatever. Alright, so we apply force with our hand. It causes the wrench and hopefully the nut to turn, and we get our bolt out. Right? So any force that causes a rotation is called a torque. Well, torque depends on how big the force is, the direction that force is acting, and where that force is applied. Right? Think of pushing open a door. Right? That's rotational motion, right? You have the door, and it's got to rotate about its hinges, right? Go try to open the door by pushing on the hinges instead of pushing on the doorknob. It doesn't work. Right? So it depends on where you apply the force. Okay? Check out those videos to see what I mean in more detail. Here's a picture. Alright? Here we got our crusted old nut trying to get our bolt out. Here's our wrench. We're applying a force, but now we're applying a force at an angle, right? So that's going to give us a little bit of torque, but that's not really going to get us a lot because all of that force is not going to be acting on that wrench, right? Being at an angle, we're losing some of it, right? Remember your vector stuff. But here, look at this. Now we've got a perfect 90-degree angle. We can get all our force pulling up on that handle, all right? Well, remember, force depends not only on how much force is applied, but also where you apply it, right? So if we can make this lever arm, or that would also be the radius of the circle once we start moving around, right? If we can make that lever arm or radius of the circle bigger, that's going to help us apply even more torque. Alright? Now, talking about rotational motion, stability becomes an issue, right? You ever wonder how the Leaning Tower of Pisa is still standing and not toppled over? Alright, well, center mass and center of gravity are pretty much the same thing. It's where all the mass and all the weight is their average position, right? So the average position of anything is probably near the center of that thing, right? Hence the dot on the tower here. Well, if you can draw a line straight down from that dot representing the center of mass to the ground, right? As long as that falls within the base of the object, it will stay stable. Now, if this Leaning Tower of Pisa was leaning just a little bit more, causing this line to be maybe, say, over here, it wouldn't be stable. It would topple over. Okay? Now, centripetal force, right, also known as radial force or angular force, right, all synonymous, is the force that causes the rotation that we've been talking about. All right? So what's causing the rotation of little Sally here twirling this can above her head? Right? It's the tension in the string. All right? So this radial force is not a new force. It could be any of the forces we've talked about prior to now. But whichever one is causing that rotation, now we treat a little bit differently. Okay? Because it's not linear motion anymore. All right? There's a couple of videos for you. Now, what does this force depend on? Well, it depends on the mass of the object, the linear or tangential speed of the object, and how big of a circle we're talking about. Okay? So we can calculate force by multiplying the mass times that speed squared, divided by the radius of the circle. Alright? And I like this picture here because it tells you where things are headed. Right? So the velocity is tangent to the circle, right? Hence the name tangential speed. Right? This arrow shows you the direction of motion. And here's the string holding the can or the ball or this object in place to go around the circle, right? So that tension is the centripetal force, right? Always pulling back towards the center. Okay? Now here's an application that you do every day. You probably don't even think about it. You drive to school, you drive to work, you drive back home. You probably go around a curve somewhere along your trip. Alright? Well, the friction between your tires and the road is what holds you in that curve. Alright, because think about it. If you've got a wet road or icy road and you're going too fast, you're probably not going to stay on the road, right? So that friction force is actually what's acting as a centripetal force in that scenario, holding you on the road. Okay? Down here we have a picture if you have bad road conditions, alright, and you don't have enough friction force to hold you in the curve, look where you're going to go. Off-road. Not good. Angular momentum is conserved always, just like linear momentum in chapter 6. Alright? So, remember, linear momentum was mass times velocity, right? Well, mass is a measure of inertia, alright? Same thing here. Angular momentum is based on inertia times the angular speed. Can you see the similarities? Alright? So, just like a net force was required to have a change in momentum, a net torque is required to have a change in angular momentum. There's a lot of relationships here. Right? You can actually use angular momentum to rewrite, or restate, I should say, Newton's first law. Okay? Momentum is always conserved no matter if it's linear or angular. Here's an example. We've got a guy holding his arms out, so his mass is distributed further from his axis of rotation, right? Which is going to give him a big inertia, right? Represented by the I here. So if we start him spinning, he's going to have a big inertia because of his mass distribution and a little angular velocity. But what happens when he pulls his arms in? Well, total momentum's got to be conserved. So by pulling his arms in, he just lowered his inertia, rotational inertia. So to keep the total angular momentum the same, that means his angular velocity's got to get bigger. And so look at him, woo, spinning around really fast. Okay? And that about does it for rotation. Alright, please watch the videos, read your textbook, and let me know if you have any questions.